All right, hey guys. Today there was a div 3, and I don't have much time. I have around like 20 minutes to do this, so I'm gonna have to go through solutions quickly. But I'll just say I did not have fun with this round because it was sort of like just spending a lot of time debugging something stupid and making some errors and stuff like that. That's not to say it was a bad round. I just did not have fun with it because I am bad and mess things up. So maybe you guys had different experiences. I guess we'll find out. But for now, I will just go over solutions as quickly as I can and try to flush things out. All right, so here you have a table that's essentially numbered by columns. That is, first you go down the columns, and then first you go like for a single column you go down the rows, and then there, and then in that column, and then that column, etc. And then we want to figure out its numbering if we were to number by rows instead, where we would go through a row and then to the next row and to the next row. So the thing to do is, first we need to simply find the cell, find the absolute coordinate, like find the row it's on and the column it's on. So if we have something like, let me just paste this in. It's terrible. But if we have something like this, then the first column is going to get the numbers 1 to 3, the second will get the numbers 4 to 6, etc. So we can find the column by simply, so if we like number them starting from 0, which may be more helpful, then we can say that this gets 0 to 2, this gets 3 to 5, this gets 6 to 8, etc. And then it may be evident that the column it's in is equal to the cell number divided by 3, and then rounded down. Or divided by what the number of rows we have, because every n rows we go into a new column. And then to find the row, we need to find the remainder of the division, because that's what the row would be. So for the row, we take the remainder of the division of x divided by n, which is x modulo n. And the answer is, for a given row, there will have been, say we're like on the third row, then there will have been 2 rows that we've already passed, meaning that, so like the answer now is, well, again, we're 0 indexing actually. So the answer, if we're on the third row, then it would be row 2 in our indexing. So 2 rows will have passed, meaning that there will be m times that number of rows cells that have passed, because each row has m cells. And then the column is simply the index of the column in the original table, because every column takes exactly 1. Okay, sure. Yeah, so basically we do that. We find the original row and column in the normal ordering of the table, and then we construct the answer from that. Okay, this problem was just a total pain for me. I'm not gonna go over statements as much. So basically, if we have some string like this, the basic idea is greedy. First, we're going to replace the first and the last characters. Then we need to find the next character to make an x such that the condition is satisfied for this one. So say k is 3. Then we start looking from the third character ahead. If it's an x, that is if it's the end, or it's some star character, then because of greedy, we want to replace the latest star character possible, because replacing an earlier one will make it so it's harder to replace star characters in the future. So we pick the latest star character, and then we replace that with an x. And then from that x now, we look k characters ahead, and then we iterate backwards, and we find the first one that can be replaced as an x, or if it's already an x, if it's the last star character, then we're done already. So really we just need to find the first and last stars, then set them to x, set these to x, and then, so now we set these to x, And then we start with the greedy. We look k characters ahead, then k minus 1, then k, until then 1, until we find the first star character. We change this to an x, and then we continue up until we get to the end. So essentially that's what's happening here. We find the first, find the last, and then set some target at the first position, then look for the next position that's an x or a star, and then if necessary, set it to an x and continue. So first we look for an x, and then we look for a star, and then set it to an x while we're not at the position of the last star. Because once we're at the last star, we know there's no star ahead, so we don't need to have any more x's. Yeah, that's basically it. So this problem is, I don't know why it's later than B. Basically, the entire point is you have some string s and some string t. You can remove some prefix of s and some suffix of s and some prefix of t and some suffix of t. And you want to find the minimum number of characters you have to remove so that the strings are equal. So if you change s to some like other string, like s naught, and t to some t naught. So first of all, s naught has to be equal to t naught, which means the length of s naught has to be equal to the length of t naught. And so you remove every character except for the characters that remain in the strings, meaning that the answer will be the number of characters you have to remove is the length of s minus s naught plus the length of t minus t naught. So if we call this answer x and we find the maximum length x such that it's a valid answer, then the answer would be s minus t, no wait, the length of s plus the length of t minus 2 times x. And we want to maximize x to minimize this quantity. So really now we just need to check, are there valid strings s naught and t naught that work for x? And really that just means what's the longest common substring among these two. And so because the constraints are so small, we can literally try, for each x, we can try every single substring. For example, we can try hell in both of these and then directly compare them. And it's going to be rather quick. It's going to be end of the fourth in total, which is fine. Okay, sorry, I can't go into more detail. I have like very limited time at this point. So for this one, yeah, basically this is standard as well. We can reduce this to the problem of on the frequency array, for example, say I create the frequency array for this, 161144, then the frequency of 1 is equal to 3, the frequency of 6 is equal to 1, and that's an ugly 3, is equal to 1, and the frequency of 4 is equal to 2. So if I create the array of only these frequencies, then removing two distinct elements is basically saying we pick two numbers and subtract 1 from each of them. And we want to figure out the maximum number of times we can do this. And so basically, the strategy is you pick the two most frequent elements and you decrease from both of them. That way you get 1, 1, 2. Then we pick the two most frequent again and we decrease from both of them. Then we pick the two most frequent again, and then we decrease both of them. There is a proof for this, probably. I'm not exactly sure how to prove it, and I don't want to do it now because I'm limited on time. But essentially, the idea is that you would pick the most frequent elements and decrease from both of them until you can't anymore. And this is always going to work. The proof is like, if this doesn't work, then there's no better answer. So the only time it doesn't work is if some element is too large. For example, say we have 1, 2, 5. Then every operation we do would decrease from the 5 and we would end up with 0, 0, 2. But like we have too many here anyway, there's no way we can do better than that. So this strategy would work anyway because it gives us the best answer. So another way of thinking about this strategy is we ask, is some element too large? If not, then we can remove everything, possibly excluding, like if n is odd, then we can't remove the last one because we can only remove 2 at a time. But if we can remove everything, if no element is too large, then we get n mod 2. Otherwise, and we know an element is too large if like we let the largest element be x, and then the remaining elements, if the total elements have some s, then the remaining elements have some s minus x. And so it's only too large if x is strictly greater than s minus x. So if this is the case, then the operations we're constrained to is this. And therefore the answer would be n minus 2 times s minus x, because we can't do more than that because we end up in this case. So yeah, that's basically it. So if this is true, then the answer we're constrained to is this. Otherwise, it's not true, so the answer we're constrained to is this. Again, we're doing this on the frequency array, so the array of the number of occurrences of each element. And then, yeah, so it's basically like solving a reduced problem. You could also just do it on the original array, where you again do the same strategy. You pick the two most frequent elements and decrease from both of them, or remove one of both of them, and it would work. Directly simulating it also would work because n is rather small, so either way it should be fine. Right, now this one is basically an exercise in like greedy. So we're guaranteed that it's possible. So at every point where the max is different from the previous one, like we can say, for example, stick a -1 at the beginning for convenience. Then for every point where the max is different from the previous one, then we have to put down this exact element, because otherwise, like, how would the max change, right? So here we have to put down a 3 because it's different from the previous maximum, which is like -1 for convenience, or 0, or whatever you want. Then this one, because the max has to change from 3 to 4, we have to have a 4 here, and because the max has to change from 4 to 7, we have to have a 7 here. Now the question is, what do we do with the remaining elements? And well, for lexicographically minimal, what we want is we want the smallest possible elements. Now notice that the maximum will only increase, meaning that if we put the smallest possible element down, it's going to work out for us. We don't need to worry about having to use that element in the future, because we guarantee that every element we put down is going to be smaller than our current maximum. Because if we can't do it so that's true, then there's no way to construct it at all, because then we would be forced to put down an element that's greater than our current maximum, and therefore our current maximum would change when it shouldn't. So really, as long as we only put down elements that are smaller than our current maximum, for example, here we can put down any element that hasn't been used already and is between 1 and 2. Here we can put down any element that hasn't been used already and is between 1 and 3, and here we can put down anything between 1 and 6. So as long as we constrain ourselves to only using these values, it's going to work out, because it's guaranteed that there's at least one answer. So really what that means is we just need some way to maintain the following information. For the lexicographically smallest, we need the smallest remaining number the smallest unused number between 1 and the current maximum. Let's just call it AI minus 1. And in the lexicographically maximum case, well, we just need the largest one. So the largest unused number between 1 and AI minus 1. So for this one, you can use simply a set, something that allows for deletions and querying the minimum. And for this one, it may be a bit more complicated. What you need to do is you need to query the maximum value that's less than or equal to some other value, for example, AI minus 1. And well, both of these, this is equivalent to saying query the minimum that's greater than or equal to the negative of this, negative AI minus 1. And so both of these operations can be supported with a C++ set. For example, in my code here, that's what I use. So to select the unknown element, I simply take the beginning value, which is guaranteed to be the smallest in the set, and then remove it. And here, I simply take the negative of the lower bound, which is exactly this. It's the minimum value that's greater than or equal to some other value. And then I erase it, because we have to erase at every point. And so the reason I'm able to use AI here is simply because AI will have already been removed since like we used it as a maximum before. So this could also be like negative AI plus 1, for example, but it doesn't have to be. It's either way it works. Really, you just need to support these operations somehow. And then when we have some unknown number, some number that isn't predetermined by the fact that it's a different maximum, for the smallest one, we query the minimum that hasn't been used, and then for the largest, we query the maximum that hasn't been used yet. And so that basically will work, and the greedy works simply because that's how lexicographic stuff works. You're always going to do greedy for it. All right, for F, basically the strategy for these kinds of problems is to just look at it for a while and see if you can find new patterns. And indeed, that is what we get. So if we draw out these edges, notice that when you have an odd vertex, the next edge is going to be to an odd vertex because both the row and the column increase, so the parity doesn't change. Then the next one's going to be to an odd vertex, then the next one's going to be to an odd vertex, and etc. And when you have an even vertex, every point the parity does change, so it's always going to be to an odd vertex. So really you end up with these chains where once you get on an odd vertex, you can't ever leave odd unless you do a manual override. And similarly for here. Now also note that because the points are distinct, they're basically independent because you have to be able to travel from one to the next, and then once you get to the next, then you have to travel from the next to the next, and etc. But like the order you're going to visit the points is going to be in increasing rows because you can only ever move down. No matter, even if you override some of the edges, you can only ever move down. So now basically, where do we end up? Say we're starting at 1, 1 without loss of generality, and we end up, for example, here. So how many is this going to take? Well, it's going to take us, we can go down here, go down here, go down here, and then we override here for a cost of 1. Now what if we ended up over here, for example? Well, then we could override here and end up with a cost of 1. Now the main idea is to find the point x such that when we start here and go down this many rows, we end up at column x. So for example, if we started here, we would end up here. So now we have a point y that we need to go to. Say for example, y was here, and this is basically the only special case. If you're at an even point and like the value r minus c, that is, you have to move diagonally every single time. If these two are equal, then the amount you have to spend is you have to override every edge because at every point you have to go diagonal. So the cost is going to be like if this is r1, c1, and this is r2, c2, then the cost is going to be r2 minus r1. Otherwise, for every override, you can make it so you decrease the point you go to by at most 2. So for example, if I override this, then I'll make it so instead of going diagonally twice, I'll end up going straight twice instead. So for every override, you can decrease x by at most 2, or you can also decrease it by 1. And so really the amount to figure out is how many times do you have to decrease by 1 or 2 to get to the value x minus y? And the answer for this is the ceiling of x minus y over 2. So that's the other case. And to find out the point where you end up at, basically you can trace the edges. So if you're at an even point, you go down 1 and then you go diagonal the rest of the way. And if you start an odd point, then you already go diagonal the rest of the way. So basically you figure out x, you figure out where you're going to end up, you figure out where you have to go, and you figure out the cost. You can check my code if the casework doesn't make sense. Okay, see if I can blitz through this one. So basically the idea for this problem is you want to find the first character. Now because you want lexicographically maximal, you want to find the largest possible first character. So we're going to iterate from z to a and basically say if this character hasn't been used yet, call this character like x, and I'll say the character z to the character a. If this character x hasn't been used yet, then we want to see if it can be our first character because we want to take the largest possible first character. So the idea is we look at the first position of x. Then we see, can this be a valid character? And And if it's going to be a valid character, then it means we aren't forced to take any other characters on the rest of this. And all that means is that for every character that's not yet used, it has at least one occurrence after X. So there are many ways to check this. What I did was I simply kept a running counter for each variable, and for each visited thing, for each unvisited character, like the characters that we still have to use, and the characters that are also in the string, then I would simply decrement the counter for every point past here. And then, so if any counter is 0, that means that all of its occurrences are going to be on this prefix. And so it means it's not possible. But if every counter is at least 1, then it means that every character has at least one occurrence on the suffix, meaning that this is valid because we're not forced to use any other characters before. We're allowed to use this character because there's a valid string that uses the rest of this. And so that's the idea with lexicographic problems also. A different strategy you can use is check if the current move is valid. That is, if there's some other sequence of moves that works afterwards. And if so, then because lexicographic is equivalent to greedy, you have to take this character because it's the largest you can take while still being valid. Yeah, so basically in code, that's what I'm doing. I'm checking this for each 26 times, so like for each possible character that can be in the string, for each character from Z to A, and then just basically check, like, decrement the counter, see if it's possible for every character, and increment the counter otherwise, and basically reset it. And we only have to check the first occurrence because note that, like, with an earlier character, we're more likely to have another occurrence on the suffix. So we really only want to check the first character. And yeah, basically greedy. Okay, so my performance in this round was like subpar. I should have done better. I spent a long time on B, although I think basically everyone did. And then messed up G for the longest time because I had the wrong idea, and then also messed up F for a while. Yeah, so it's a bit unfortunate, but I mean, I guess it's the best you can do. So I'll leave it at that. Hope you enjoyed the round. Wish I'd spent it less time so I could have a bit more time for solutions, but it is what it is. So, yeah. And again, it's school constraining me to do this because I don't have that much time. Like, I have a class starting very soon, so it's the best I can do. Goodbye.